Hi everyone, this is the first video in a new mini-series I'm making on isolated voltage measurement, which is a really interesting problem that crops up in quite a few fields. Let's get started. So I just want to start by briefly considering what is isolation and why do we need it. Probably the most common need for isolation is for safety. For example, in EVs there's normally a low voltage and a high voltage system. So the high voltage will power the motors, and that'll be your big battery when they say 70 kilowatt hour or something like that. And then the low voltage battery will be usually just a normal 12 volt car battery, and that'll do basically everything else: headlights, infotainment system, stuff like that. The reason I'm showing this is because this is the inverter from the Formula Student car, and that has a similar system. So there's a small 12 volt battery that powers the dashboard, telemetry system, stuff like that. And then there's a big 600 volt battery which connects to the inverter, and that's fully isolated from the car, whereas the 12 volt one, the ground terminal of that battery is connected to the whole chassis, just like in a normal road car. And the reason it's fully isolated is that then means neither of the terminals are referenced to ground, so you can touch either one of them on its own, and theoretically nothing bad will happen. Whereas if you also connected the negative terminal of the HV battery to the chassis, then all you'd have to do is touch the positive terminal, and you're probably going to be touching the chassis if you're working on the car, so then you'll get zapped. But that brings the problem of how do we measure a voltage in a fully isolated system? If you're just testing it, you can simply connect a handheld multimeter, and they're battery powered, they're fully isolated. So the potential of the circuit inside that multimeter will match the potential of the high voltage that you're probing, but it doesn't matter because the multimeter's not connected to anything else. Whereas what we want to do is we want to measure our, for example on this inverter, our 600 volt input. We want to measure the voltage of that, but we don't want any physical direct electrical connection between that and the low voltage side, which is where our data processing is, that will deal with that voltage and tell us whether it's too high, too low, that kind of thing. The same is also true for current measurements, but those are in a way a bit easier, so that's why I wanted to focus on voltage measurement for this new series of videos. Heading back over to my seemingly random pile of components, what we have is a breadboard, which is, I'm going to use a few of these to build my circuits, and then an isolated DC to DC converter, which in this case I'm just using a module because otherwise it's quite hard to do. And you can see this particular one is an 0505 if you look at those numbers. That means 5 volts in, 5 volts out, but it's fully isolated. And these are really nice. They're actually very affordable as well, even a high-end one like this. Then we also have this chip, which I'm using to generate a PWM signal. So you've probably seen from the title, the way we're going to do this in this video is using pulse width modulation, which I'll get into more detail later on. And then finally this is an optocoupler. So there's an infrared LED in here and an infrared photodiode, and basically when you turn the LED on, the photodiode conducts. But because it's using light, there's no direct electrical connection, which is exactly what we want. I'm also going to need a few other components, wires and things, which I'll get later. Before I get started building my circuit, I just want to cover how I'm going to test this. So I'm going to generate a voltage on the isolated side using this function generator, which has a DC output mode, which means I can just type in an exact value and it should output that exact voltage. All of my equipment is very old and out of calibration, but it should still be good enough for this video, especially as the main thing we're concerned about in this case is linearity, which again I'll go into later. Then we'll be measuring the output of that on this Solitron multimeter and powering the whole system from this TTI power supply. Later on I'm also going to be doing some noise measurements on my oscilloscope, which is up here. So I'm going to build this circuit in steps just to make sure that if something goes wrong I know exactly what it is. The first thing we want to do is generate a pulse width modulated signal based on the amplitude of our input voltage. Now although the examples I mentioned are all high voltage, there are some times when you only need to measure a low voltage, but it still needs to be isolated. That's quite common in the medical field. This chip I'm going to be using has an input range of 0 to 5 volts, or less than that if we connect the VREF pin to something else, although I think we'll just connect it to VDD at 5 volts for this. If you wanted to measure, let's say 0 to 500 volts, you just connect a potential divider before this input because it's very high impedance. So it doesn't really matter that we're only testing up to 5 volts, because boosting the voltage or reducing it down, that's all very simple stuff, and it won't affect the key parameter, which is linearity. So I'll start by just powering this chip up, and then we'll probe the output from the oscilloscope and have a look at what the PWM is actually doing. For anyone wondering, this isn't actually a discrete PWM chip, although that's what you'd use if you wanted to build this circuit in reality. This is actually a PIC12F683, because I have a huge amount of those, and unlike the majority of PWM chips that I have, this doesn't require any external circuitry, so it just simplifies things for this demonstration. That does mean that this is technically digital because it's getting fed into a 10-bit ADC, then getting fed into a 10-bit pulse width modulator. But that shouldn't affect our results too much. And 10 bits is pretty decent, to be honest. The next thing I'm going to do is connect the VREF pin high, so that's just going to 5 volts as well. Then I'm going to get our analog input and connect that to the output of the function generator. This function generator has quite a loud fan, so hopefully when I turn it on it's not going to be too disturbing. Finally, I'm going to connect the oscilloscope to the output so that we can have a look at the PWM coming out of it. So just to be clear, there's no isolation going on here at the moment. All we're doing is generating a PWM signal where the duty cycle is proportional to the amplitude of the input voltage. That's just the first step to this PWM isolation technique. Hopefully this function generator isn't too noisy. Now I'm going to switch the output to DC mode, and I'm going to turn on the PIC. So it should be, if I do this, is this in millivolts maybe? Yes, it's millivolts. You can see the exponent here. It's quite a nice function generator, this. Let's increase the range. So now that should be 1 volt, and it's looking like on here we've got 2 volts, but who knows? I guess that's because of the termination. There's no 50 ohm load resistor. So I will add that now, just so that the voltage is what it says it is. And the reason why that's the case is because what this means when it says it has a 50 ohm output impedance is basically, if you imagine it's got a 0 ohm output impedance internally, and then there's a 50 ohm resistor in series just before the signal comes out, then the idea is that whatever you plug it into has a 50 ohm resistor on the input, and that means the impedances match, which is very important for high frequency stuff, but I'm afraid I don't fully understand it, so I can't say much more than that. Now don't tell anybody, but this is actually a 47 ohm resistor, not 50, but that shouldn't make too much difference. And I'm just adding that in between the input and ground, so basically on the output of the function generator. 1 volt set on the output, we're almost getting 1 volt on the input of the multimeter. But you can see on the scope screen here we've got PWM, and as we increase this, we go from 1 volt to 3, 4, and then 5, it's almost entirely on, as expected. You can see this isn't quite 5 volts, that's because of the 47 ohm resistor. I guess I'll swap it for 200 ohm resistors in series, that would make more sense. There we go, that's much closer to 50 ohms now. And when we turn it up, yeah, 5 volts, it's almost entirely on. And we can go down to 0 volts. There we go, 0 volts, it's almost entirely off. And basically the idea with this is that pulse width modulation is the concept of turning something on and off very quick. And if you change the ratio of how long it's turned on to how long it's turned off, then you can change the average value. So theoretically, if we set this up so that if I do a 2.5 volt input, 2.5 volts in, this should be a 50% duty cycle. So that means half of the time the signal is on and half the time the signal is off. So then if you smooth that by passing it through a low pass filter, you should get exactly half of the high voltage, which in this case would be 2.5 volts, which is our input. And that's basically the concept we're going to use to pass it through isolation. So these optocouplers are designed for digital stuff, so they're best when you're just turning them on or off. We'll be looking at analog use of them later in the next video. But yeah, the basic concept with this is we're feeding in 2.5 volts, which is half of the 5 volt input range. So then we have a signal that's on half of the time. Then we pass it through this, which then gives us the same signal but fully isolated because it's using light instead of copper. And then we have the same signal on the output, 5 volts half the time, 0 volts half the time. So then if we smooth that, we should get 2.5 volts, which is the same as our input. So how about, before we add in any isolation, let's have a go at smoothing this signal and see whether we get the same as our input on the output. For that I'm just going to grab some random capacitors and resistors. So in this case the first thing I'm going to try is this 22 microfarad capacitor, and let's try this 10k resistor. Now one thing that's probably worth pointing out is that just smoothing it like this only really works if you have an output that can both source and sink current. For example, if you had an open collector output on something, which is exactly what this opto isolator is going to have, they can only sink current. So what you'd do is you'd connect this, it would pull the capacitor voltage low, but then when the signal turns off, it would never rise back up again, unless you added a pull-up resistor, which is what we're going to have to do. But in this case, this microcontroller can both source and sink, so we don't have to worry at the moment. So I'm just going to connect this capacitor to ground, and then the other end of it is going to be connected to the PWM output through a resistor. And then that should go output through the resistor into the capacitor. That forms a simple low-pass filter. So I'm going to move the scope probe now to have a look at that, and we'll see what we've got. So I'm looking at the output on the scope now. It looks nice and smooth, although it does also look a little bit lower than 2.5 volts. So I'm going to adjust my position a bit so that I can fit in 1 volt per division. That will give us a bit of a better view. No, it does. That looks pretty good actually. I think that's 2.5 volts. And we can test. Let's try going to 2 volts, 3, 4, 3, 2. I'm going to get the camera a bit closer so you can see an interesting side effect. And what that is that because the time constant of the low-pass filter we're using is very high to make it nice and smooth on the output, it takes quite a long time to adjust, which in some cases isn't a problem, because in fact in some cases, let's say you're measuring a DC bus of a tractive system in an EV, there's going to be quite a lot of noise on it. So if all you want is a nice smooth voltage, you'll probably put it through a low-pass filter like this anyway, so then it's really not a problem. But if you're wanting to measure an AC signal, for example, then this becomes a real problem using this technique. We'll get into that a bit more later on when we test the bandwidth of this system. But as you can see, right now we're at 2 volts output. Well, I'll get it to measure it so you can actually see that. There we go, average voltage there. So we're around 2 volts. Now if I turn it up to 3, can you see how it takes quite a while to change? That's 5, 4, 3, 2, 1. Now what I'm going to do, to prove that that is because of the output filter, is I'm going to swap the resistor for a 1K, which will make the response a lot better, but hopefully it's come across in the video. There's now a little bit of switching noise on here, which is obviously undesirable. But watch how fast it responds now. 1 volt, 2 volt, 3, 4, 5. 4, 3, 2, 1. Crazy. And that's a tricky trade-off that we have to consider for this particular circuit. You could do it with some maths, work out the exact values you want, or you can just try a load of different values. As I say, depending on the scenario, you may want faster response, or you may want low noise, and not care as much about the frequency response. Heading back over to the circuit, I have now stripped it all down, because it's time to add in the opto isolator. I'm also going to add in the DCDC at this point, so that I don't have to use 2 channels of my power supply. So I'm going to move the microcontroller up to the top, that's generating our PWM. Then we've got our optocoupler, and then finally, unfortunately, the DCDC can't straddle the gap of the breadboard, so it's going to have to just sit here, which is annoying because it's not going to look very isolated, this, but you've got to trust me that it's fully isolated. Another problem I have is that the voltage that's coming out of my function generator is referenced to ground because the BNC connectors on the function generator are grounded. That's also true of the scope, which means when I'm probing the output while the input is being fed by the function generator, both sides are grounded, which means they're not actually isolated. But we're going to ignore that for now because that's just to do with the way I'm measuring stuff. If you put this in a real scenario where you had 2 isolated circuits, it would be fine. In case you're interested as well, this opto isolator is a 4N25 from Vichy. They're quite old now, but pretty decent. I think it's got 5 kilovolts of isolation. And this DCDC is made by Murata. As I said before, it's 5 volts in, 5 volts out. You can get other variants with bipolar outputs, higher voltage ranges, higher power, because I think this is only 1 watt, which is fine for this. Now this DCDC, according to the datasheet, is meant to have a little LC filter on the output to get rid of switching noise, but I don't think that's going to be that critical in this circuit, so we're not going to bother. Right, here's the DCDC wired in, so you can see these two connections are the 5V input, and then these two are the isolated 5V output, which is going onto the other side of the breadboard. That isolated output is then going to feed our PWM chip, and the output from the PWM chip is going to go through the optocoupler, which is going to require a resistor because internally, as I said, it's just an infrared LED feeding a photodiode, and that LED needs a current limiting resistor. And the datasheet says that LED can handle up to 60 milliamps, so I'm going to use a 100 ohm resistor between the output of the PWM chip and the anode of that LED. Then the cathode of that LED is just going to go to the isolated negative rail. Now all that's left to do is connect up the output of that optocouple. So as you can see on the datasheet, internally there's a photo transistor, and the one circuit that they show, which they call the switching schematic, doesn't connect to the base, it just connects the emitter to ground, which is what we're going to do here, and that's ground on the non-isolated side. And then the collector is pulled up through a resistor. So I'm going to use 1K for now, and we'll see if there's any issues with that. There we go, so we've got 5V from the power supply. That then goes into the isolated DC-DC converter, which creates another 5V rail over here that's completely isolated from this one. So that means I can connect the positive or negative of this to the positive or negative of this. Nothing would happen because they're completely isolated. And this DC-DC allows for up to 2000 volts between these two potentials without any issues. Then the isolated side powers our microcontroller, which is producing our PWM signal. And that PWM signal then goes into our photocouple here. The output of the photocouple is then connected in an open collector configuration with a 1K pull-up resistor. So let's get the scope on again and have a look at that output. So here's the output of our photocouple. You can see when I change the input voltage, it does change. It is inverted though, so right now this is 1V and it's on for 80% of the time. And then if I go up to 4V, it's only on for 20% of the time. That's because of the open collector configuration of the photo transistor, which acts as an inverter. But that's fine, that would be very easy to change in a circuit, or in this case we're just going to invert all our values. Hopefully you can see here this signal does not have the best rise time, so what I'm going to do to improve that is swap the 1K pull-up resistor with a slightly lower value, 470 ohm resistor. If I go any lower, you start to get issues with the photo transistor not being able to pull it down all the way, and that rise time looks a little bit better. That's probably as good as we're going to need. Now all that we need to do is add our low pass filter to the output. So because the pull-up of the open collector output of the photo transistor is only 470 ohms, we want a resistance that's a lot higher than that that's to feed into our capacitor, to prevent any issues caused by the fact that it will be able to sync better than it will source. Because when it's sourcing through a 470 ohm resistor, whereas when it's syncing, it's going straight through a transistor that can probably turn on with lower equivalent resistance. So because of that, I'm going to use a 10K resistor and a 1 microfarad capacitor. And like magic, there they are in the circuit. Now let's have a look at the output. So back at the scope you can see 1V output. As I said, this is inverted, so I'm actually feeding in 4V at the moment. And it's 1V because it's doing 5 minus the input. So if I set this to 3V, we should get 2V on the output. There we go, 2V in, 3V out, 1V in, 4 out, and no volts in, 5 out. Perfect. So that's our circuit fully working, so I think now it's probably time to do some characterization. First and foremost, what I want to characterize is the linearity, so I want to see if I feed in 1V, what do I get? If I feed in 2, do I get double? Because it doesn't matter if I'm only getting 90% of the output consistently, because then you can just add an op-amp or something, add a bit of gain, and you fix that. So what I'm going to do is I'm going to test this at loads of different voltages and make a nice plot of that. And then also what I'm going to do before that is feed the function generator straight into the multimeter to get a control, just to make sure that the output of the function generator is somewhat linear. And if it's not, we'll normalise our plots to the output of the function generator. So what that means is it's now time for you to watch some sped up footage of me doing all that. Now this is where a wireless keyboard really comes in handy. So I'm just going to be changing the value on here, typing it in, pressing enter. I'm going to go through 51 values, so we're going to go from 0 volts right up to 5 volts in 100 millivolt increments. And we're going to repeat that for the direct measurement of the output of the function generator and the output of our nice circuit we've made. And we're going to repeat this testing method for future videos on different methods of isolated voltage measurement. And then hopefully at the end of the series we can have a nice plot showing the advantages and disadvantages of the different methods. Now, if you were going to do this properly, you'd use an automated test system, so your voltage source and multimeter would both be remotely controlled by some code you'd write that would, say, change the voltage twice a second and sample it, maybe sample it a few times and take an average. I think both that multimeter and function generator have RS-232 interfaces, but I really can't be bothered to work out how to use them. This does end up taking quite a while though, and I think through this video I ended up spending almost an hour just pressing buttons and typing numbers. So make sure to subscribe if you want more great commitment like that. Now let's repeat that again, but this time with the output of our circuit. So it's going to be fully isolated and it'll be digitised, well, turned into PWM, then filtered, smoothed, and we'll see how much that affects the linearity of everything. You might notice that the value on the multimeter counts in the opposite direction to the output of the function generator, and that's because of that inversion I mentioned earlier due to the open collector output of the phototransistor in the opto-isolator. I've entered these values directly into an Excel spreadsheet, and to compensate for the inversion, what I've done is I've subtracted every value from the maximum value, which then negates them so that they're increasing in the correct direction and adds on that offset or accounts for the negativity. I've decided I'm also going to do this another time, which is going to be the same RC smoothing filter, but it's going to be directly on the output of the PWM, so then hopefully we can tell if there's non-linearities. Does any of it come from the PWM side of it, or is it all from the photodiode side of it? Any non-linearities that we do find on the output side after passing through the photodiode, they're probably most likely caused by the combination of the current that we're running the LED at and the value of the pull-up resistor used on the output, because combined together those two determine the rise and fall times of the output. That's because if we drive the LED harder, the phototransistor will turn on stronger and pull the output lower faster. If we use a lower value resistor for the pull-up on the output, that will pull it back up faster. But if we use too low, then it'll never get pulled down to zero. If the rise and fall times are very slow, then at low duties you'll start to get weird stuff happening. So for example, if you're on just a 5% duty cycle, let's say that equated to a 10 microsecond on time, but the rise time is 20 microseconds, then it won't even rise in time. So that means once you average it out, your value will be quite a bit lower than what it should be. This particular photodiode, as you saw earlier, doesn't have the best rise and fall times, so as you'll see in a minute, that's sort of the reason why this isn't perfect. But if you buy a commercial isolation amplifier which uses this same pulse width modulation method, they'll have very high quality photodiodes in. So here's our first plot, which is showing the output of the function generator against what it says it should be, just to check that the output voltage of that is fairly linear. And you can see it's got very good linearity. The only issue that you can see here is that the voltage is slightly higher than it's set to, and that is probably because the 200 ohm resistors I'm using in parallel to give our 50 ohm termination, they're quite poor tolerance, so that's probably because the 50 ohms is actually like 53 ohms or something like that. That would let the voltage creep up slightly higher than it should be. So what I'm going to do in the next plot is plot it against this voltage instead of what it's set to, although that shouldn't really make too much difference. The key thing is that this line is perfectly straight, which is exactly what we want. Next is the plot of the output, both before and after passing through the optocouple. So you can see, looking at the blue line, the output directly out of the microcontroller once it's been turned into PWM, that is pretty much perfect. It starts at 0, finishes without any kind of weird curl at the end, and it's pretty much linear the whole way. Then looking at the output of the optocoupler, that follows it really nicely too. There's a little bit of error, but overall it's pretty nice, up until the top where it starts to curl off, and I think that is probably due to the rise time, not the fall time. But if you were just looking for a general voltage measurement, this circuit is great. And it's a lot cheaper than buying a special voltage transducer, or even most isolation amplifiers would cost more than this circuit. So it's something to consider if you have a high voltage or even low voltage that's isolated and you want to measure it. So that's the end of our linearity tests. Now what we're going to test is the bandwidth of the system, which in this case is heavily affected by the values of the RC filter on the output. The values used here work quite nicely to get rid of pretty much all of the switching ripple, so I won't be changing those. You could reduce them to get greater bandwidth, but then you'd have more switching ripple, and then if you wanted to sample it, you'd have to filter out that switching ripple, which would then bring you back to where you started. As I did earlier, I'm going to start by measuring the direct output of the function generator, just to make sure the amplitude stays fairly constant with frequency. And for the sake of my sanity, we're going to start at 1 Hz and go up, sort of doubling, a bit like the controls on an oscilloscope, so it'll go 1, 2, 5, 10, 20, 50, and so on. This function generator will do up to 50 MHz, but I will be very surprised if we need that for any of the techniques we're going to be using. I'm going to be using the oscilloscope to measure the amplitude this time, which doesn't give us a huge amount of resolution, but it should be enough. And now it's time to sweep through frequencies. So for this I did basically the same thing as last time, except instead of changing the offset on the function generator, I was changing the frequency. We're mostly interested in frequencies up to maybe 100 kHz. That's usually the upper limits of the majority of lower end commercial voltage transducers, which is the only thing I'm really interested in trying to compete with at the moment. If you're getting into the megahertz, you're more looking at some kind of high-end differential probe or something like that. And also, of course, my whole circuit's on a breadboard, so anything definitely over 1 megahertz is going to start to have issues being on a breadboard, especially with the very cheap, thin jumper wires I use. Right, so that's the output directly from the function generator. It seemed pretty much perfect up to a few meg, and then it went a bit weird, but we won't need that higher frequency, so that is absolutely fine. Next I'm going to do the same thing with the output of our circuit, so that's after it's been pulse width modulated and once it's been isolated and smoothed again. Then after that I'm going to redo it just out of the pulse width modulator to again see if the opto isolator is reducing the bandwidth at all. Here's just more of the same. What I had to do later on is when the output amplitude started to get low, I changed the scope to AC coupling so that I could actually zoom in on the signal without the DC offset just being enormous. Another thing that was interesting to notice was that around 1 kHz, the wave stopped being sinusoidal and started being triangular, which I guess is a result of the pulse width modulation used. That's probably just because I was zooming in so much that I could see the ripple on that RC output filter, whereas before I couldn't see it because I was zoomed out to see the full sine wave. I'm now at 2 kHz and the output has pretty much reduced to nothing, so I'm not going to bother doing this any higher frequency than that. That is around the switching frequency, so you couldn't really expect it to have a bandwidth greater than the switching frequency. That wouldn't make any sense. Finally, let's repeat this with the smoothed PWM output before it goes through the Optocoupler to see if there's any difference. This one was pretty much exactly the same as the previous one. The effect of the Optocoupler on the frequency response when the switching frequency is this low is very minimal. If I was still using a slow optocoupler like this, with a much higher switching frequency however, then there would start to be a difference between the two of these readings. Right, and that is all of our testing done. Brilliant. So this first plot is just looking at the output amplitude of the function generator dependent on frequency. You can see it's fairly constant up to around 100 kHz, and then it starts to go a bit weird. It looks particularly weird on this plot because I'm using just linear interpolation between the points, of which there aren't very many. And I imagine the frequency response up to 100 kHz is probably a lot smoother than that. It just looks bad because of my probing technique. I do remember a while ago I fed the function generator directly into the oscilloscope with proper 50 ohm termination and a BNC cable, and it had a pretty much flat frequency response from millihertz up to the full 50 megahertz. So this is probably mostly due to issues with the breadboard and the way it's been probed. But as I mentioned earlier, it's flat up to 100 kHz and that's all we really need. And then this final plot is looking at the frequency response of the output from both the PWM modulator and the photocoupler. You can see just based on these few data points, it appears that the optocoupler does have a slight effect on the frequency response, as the orange line is ever so slightly lower than the blue line at the majority of the points on the graph. You can see though both of them exhibit a roll-off starting at before even 10 Hz, which is not great. As I've mentioned a few times now, that's mostly due to the RC filter on the output, but without that you'd just get the PWM, which would basically just be pure ripple. So you can adjust these values, you can get a better frequency response but worse output ripple. The best thing you can do really is increase the switching frequency, because then you can reduce the time constant of this RC filter without introducing too much ripple because the frequency is so much higher. If you bought a proper isolation amplifier using pulse width modulation like this, it would probably be in the high hundreds of kilohertz, which would significantly reduce this problem and increase the frequency response to probably a few kilohertz, which is good enough for the majority of applications, to be honest. What we're going to be looking at in the next two videos is alternative methods for this isolated voltage measurement problem that don't have this inherent bandwidth limitation that the pulse width modulation method uses. That's it for today. Well done for making it to the end. I hope you enjoyed watching this video as much as I enjoyed making it. This is a really interesting topic and I can't wait to record the next two videos. Anyway, don't forget to subscribe, and until next time, goodbye.